Jai Hind students, today we are going to understand ABU algorithm. This ABU algorithm is used to find out the given decomposition is lossless joint decomposition or lossy decomposition. You know, when a decomposition of a relation is in 2-part or 3-part, 4-part, so how we come to know that decomposition is lossless or lossy? Now, if decomposition is binary decomposition, it is very easy to find out that decomposition is lossless or lossy. In case of binary decomposition, what we need to do basically, we need to check this condition for each and every relation R1 or R2. We need to find out this functional dependency should be exist or this functional dependency should be exist. Right. So it is very easy to find out the relation decomposition is lossless or lossy in case of binary decomposition. But problem arises when the decomposition is having more than 2 parts. Right. Let's suppose we are having a relation schema R and then let a relation R which is decomposed in R1, R2, R3 and so on. R is having attributes A1, A2, A3, AM. Okay, and a functional dependency set is F. So this is our assumption for the algorithm. Now we are starting the algorithm step 1. Okay, so in the step 1, what we will do, we will make a metric. Okay, so make a metric M of dimension M into N, where columns are corresponding to attributes. So how many columns will be there? At most M, because we are taking M attribute, right? So value of this column, or we are taking this one counter J, will vary from 1 to M, right? Similarly, rows are corresponding to projection. We are taking counter I here. So there may be M rows. If we are having 3-part decomposition, three relations we got after decomposition, then the value of N will be 3 at most. Right. So now we have made or a metric of M cross N dimension. Now it is time to initialize this metric. Whenever we want to initialize a metric, we need to apply 2 for loops. Okay, so here also we are applying 2 for loop, and in these 2 nested for loops we are writing the condition AJ is the element of Ri, then M I J will be AJ, else M I J will be B I J. Right. So by this way we will initialize the metric. For initializing the matrix, we need to apply two loops in nesting, and condition is what? If AJ, it means any attribute, is the element of that particular part of relation R1, R2, R3, then Mij, that element of the metric, will be denoted by AJ, else that element of matrix will be denoted by Bij. So here we are using only one suffix, that is column number. Here we are using two suffix, row number and column number both. Okay. So the next step, 3, whatever value we have taken in M, we need to save those values. And then for each functional dependency X tends to Y, which are exist in a functional dependency set, what we will do? Okay, for each and every functional dependency, we need to check if any two rows are same for the value of A, then, or any two rows are same or match for the value of A, then force those rows to match the value of Y, here X. So if any two rows are matching for the value of X, then we need to force those rows to match the value of Y, right? Because this functional dependency exists. So we are using the rules of the functional dependency. Okay. Now the last step, test for the lossless joint decomposition. If any of the rows of M containing the all A values, means lossless joint decomposition, otherwise lossy decomposition. So this is what the algorithm. Just recap the algorithm. Here we are understanding the ABU algorithm to find out the decomposition of a relation is lossless joint decomposition or it is lossy decomposition. So with that algorithm, we are assuming that R is a relation we are having that is decomposed into some part more than 2, and that R is having some attribute. Let's suppose M attribute A1 to AM. F is the set of function dependency. We are starting with the step 1. Make a matrix M of dimension M cross N. Here columns are corresponding to the attributes, and attributes, how many attributes are there? 1 to M. So the counter we have taken J will vary from 1 to M. rows are corresponding to the projection. How many decompositions are there? Let's suppose 3. So how many projections are there? 3 projections are there, and the value of counter I taken for the rows will vary from 1 to n. Here for this 3 part will have 3 rows, right? Then the step 2, initialize M as follows. How we need to initialize, how we need to give the value to each and every element of the metric? By applying nested for loop. So we are applying that nested for loop, you know very well. And what is the condition to initialize? If AJ, that particular attribute, is the element of that particular part of that particular projection, you may say, then Mij, that particular element, will be written as AJ. A and the suffix is J, column number. Else Mij will be Bij. Here we are taking the suffix I and J both, row number and column number both. Okay. Then next step is save that matrix. Fine. For each and every functional dependency x tends to y, if it is, we will check if any two rows are matching for the value of x. So what is the meaning of this functional dependency? If we are having x, we can determine y, or we may say that y is functionally dependent on x. So if we two rows are matching on the value of x, we may write y instead of x. That's why here we have written that force those rows to match the value of y. That is very obvious. Okay, and the last step. For each and every function dependency, we will repeat this step. Fine. Then the last step, test for the lossless decomposition. We need to check the metric if any of these rows of M containing the all A values, right? All A values. It means lossless joint decomposition, otherwise lossy decomposition. So this is the algorithm. It is having 4 easy steps. We can find out very easily the given decomposition is lossless or lossy. It may be applied on binary decomposition, but binary decomposition is very easy to check it is lossy or lossless. So in general, we apply this on more than 3 or 4 decomposition, right? Okay, so now I'm taking a question here. Here a relation schema is given named SP. It is having 1, 2, 3, 4, 5, 6, 7, 8 attributes. So in this given relation, we are having 8 attributes and we need to find out the decomposition is lossless. Okay. SP is decomposed in these 4 parts, right? So SP is given relation with 8 attributes. So we need to find out this lossless or lossy, and these are the decomposed parts. Okay. So how many relations we are having here? 1, 2, 3, 4. So after decomposition, we are getting 4 relations, and the functional dependencies hold on SP. The given relation are these. So these 4 functional dependencies are given to us. Okay. So here on this page, we can make the matrix. So for making matrix, we are taking the attribute name as hash, as name, as city, p hash. This is nothing but the p name, price, and quantity, right? 1, 2, 3, 4, 5, 6, 7. 1 is missing. State. So 1 is missing. I'm writing that. Okay. Okay. So S hash, S name, S city, and then state. Just a minute. Erase. Okay. date. Okay. Now okay. So this is J, and now we are taking I. So this is J, the attributes given to us in this given relation, and here we are taking the projections. Part SPN. Values will be 0, 1, 2, 3. Here 0, 1, 2, 3, 4, 5, 6, 7. Okay. So these are the values. Now we need to initialize each and every element, right? So while initializing, we will check this S city and S state. Okay, otherwise, so we are having only these two attributes in this part. So in this part, when we will fill, so only these two attributes are there. So we will write B00 here, B01 here, okay, and this will be filled as A, this also filled as A, and column number will be the suffix. Otherwise, all values will be filled with Bij, I0, J5, Bij, I0, J6, Bij, I0, J7. Similarly, we will fill all the rows. Okay. So in this, S hash will be filled as A because this attribute is presenting is here only. Okay. So this we have taken as P name. Okay. So right. So here we'll write A0, S name, P name. So here it is P name, it is S name because this is the supplier's information. So here we will write S name, right? S. This is nothing but the S name. This is the part information, so P name. Here, supplier information, S name, part information, P name. This is just a typing mistake. Okay. So here we can see that S hash A0, S name A1, S city sorry, not 2, not 3, it is basically 2. Okay. So it is 2. So only 3 attributes are here. All other attributes will be written as B with the suffix row number 1, 3, 4, 5, 6, 7. Okay. Similarly, we'll fill for this part P hash A4, P name A5, price A6. Only these 3. Other will be filled as B. Right. We will write the suffix 2, 2, 2, 2, 2, 0, 1, 2, 3, and 7. Similarly, we will fill the last row. S hash will be filled with A with the row column number. P hash will be filled as A with the column number. Quantity will be filled as A with the column number. All other will be filled as B. Third number, this 1, 2, 3, 5, 6. So by this way we have filled all the matrix element. Now we need to up to step 2 we have done, and for the step 3, what was the step 3? For each and every functional dependency given here, we need to check if two rows are same for A values, right? Then we will force them to, for each and every functional dependency, we'll check if there are two rows match for X, then we will force them to write or replace by Y. So for this functional dependency, we will check first S hash, this functional dependency exists here. So okay, we'll check A0, A1, A2. A0, yes, this A0 is here, A1, A2. So if we are having A0, we can determine, if we are having S hash, we can determine these two. So here A0, so we are having, for A0 we are having A1, A2. Here also in this row we can check this A0. So what we can do, we can replace B values with A1, A2. Okay. So by this way we have replaced two values. For this functional dependency, we can see here A values. If we are having S city, we can determine the state. Okay. So we are having here A2, so we can determine A3. So here also we are having A2, so we can determine A3. So this will be replaced. Right. Okay. We'll check for this functional dependency. P hash, P name, P price here. So if we are having A4, we can determine A5, A6. Here also we are having A4, so we can determine A5, A6. A5, A6. Right. Okay. So again, we have checked these all the functional dependencies. Here also we can check that A2, we are having A2, we can determine A3. Here we have checked. If we are having A2, we can determine A3. Here also we are having A2, so we can determine A3. So the last row, we can check. This is A, this is A, this is A, this is A, this is already A, this is A, this is A, this is A. So this last row will come as A. So whenever we get this last row as A, we may say, what is the test for the lossless joint decomposition? Last step 4. So we will check if any row is containing all A values. It means it is lossless joint decomposition. So this is for the ABU algorithm. Just have a recap. We have started from here. R was our relation which are having A to M, A1 to AM attribute, and F was the function dependency set, and our relation is decomposed in 3 or 4 projections. First, in the first step, we need to make a matrix of dimension M into N. Here columns are corresponding to the attributes and rows are corresponding to the projections, number of partitions, decompositions. And in the second step, we have initialized the value R as follows. How we have initialized? If any decomposed part is having that attribute, we will fill that the corresponding element with A's with the suffix of column number. And if it is not the part of that relation, then we will fill it with B with the suffix of rows and column numbers, right? And then at last, for each and every function dependency, we need to check if 2 rows are matching for the value of X. Then we need to force those 2 rows to match the value of Y. That is very obvious, right? In the step 4, we need to check any of the rows containing all A values. It means that decomposition is lossless decomposition. Then we have taken this example. In this example, this was the relation in which we were having 8 attributes. So we have taken these all A attributes in the at the column side. So how many columns are there? 1, 2, 3, 4, 5, 6, 7, 8. So we are having 8 columns. Numbering started from 0 to 7. Right. And then how many decompositions are there? 1, 2, 3, 4. So 4 parts are there. So we have taken projection as a rows. So first projection, second, third, fourth. 4 projections starting from 0 to 3. Right. Now we need to fill these values. We have filled these values according to the rule. In this relation, we can check that we are having S city and S state. So whenever the S city and S state is there, we will fill with A's. All other will be filled with B's with proper suffix as per the rules. In this, we can see that S hash, S name, S city. S hash, S name, S city. These 3 will be filled with A with the suffix of column number. All other filled with B. And similarly, we will fill all A and B, right? Then, for each and every functional dependency, we need to check if there exists A value in a row and we are having A values in that side also. Then, we will force the other row to have that A value, same A value, right? So for first functional dependency, we have checked for this. So this functional dependency was here. So for A0, we were having A1 or A2. So here also for A0, we may have A1 and A2. So we have crossed these V value and made that first A. So this is converted. And here also we have checked that if we have A2, then we can determine A3. So here also we are having A2, so we can determine A3. Same. Here also we have checked this. Right. Here also we have checked that if we are having A4, then we can determine A5, A6. So in this row, this X value is matching. So we can force for the Y value. So these are the Y values. So we have crossed these B values and B5 and A5 and A6 is written instead of that. And here also we are having A2, then we can determine A3. So if we are having A2, by crossing them again, we can check that we have got this A2, then we can write A3 here also. So by this way, we got a row which is having all A values. So we conclude that it is the lossless joint decomposition. So by this way, dear students, we can find out the given decomposition is lossless and lossy. This ABU algorithm is very useful in DBML. Thank you so much. For any query, you may contact me. Thank you so much.